All right, let's go. So big ideas are the idea of area under a curve is the main problem we've been looking at. And then with area under the curve, we've been using Riemann sums. So some kind of generic function. You want to know what is that area in here. And we find it by making a bunch of rectangles. And the rectangles should have an equal width that we call delta x. And then we can find the height of a rectangle. That would be f of xi star. Yeah. And so the area of any one of those rectangles right there, some change in area, is the width of the rectangle times the height of the rectangle. And then we add all of those up. And you're going to need to be able to set up some of these for me. And the xi star, that's just some x value in the interval. Could be the left one, could be the right one, could be the middle one, could be any one at all. And the hardest part of these is usually coming up with the formula for the xi's. And then ultimately, what we want to do with that is we want to be able to take the limit as n goes to infinity. If n's going to infinity, that means delta x is going to 0 at the same time of this sum. And this limit right here, that's the definition of the definite interval. So that right there, if we can figure it out, is the integral as x goes from a to b of this function. And that's that notation again for the definite interval. Again, that assumes I get some starting x value over here that I call a and some ending x value over there I call b. So we'll just do a couple of examples of setting up a Riemann sum for some simple functions. And then we discovered through the fundamental theorem of calculus that it turns out the antiderivative problem is the same problem as this, right? Which makes our problem our life a little easier because that means we don't always have to find a Riemann sum. So let's try one of these. Let's say we have f of x equals 2x minus 1. And we're going to do that on the interval from, say, 1 to 4. So I want to set up a Riemann sum to approximate that area right there. First thing you should do is make a sketch. So either whip out a calculator, or if it's easy enough to do on paper, I think this one's easy enough to do without a calculator. -1 down there, 1, 2, 3, 4, 5, 6, 7, up there. And then 1, 2, 3, 4 over there. So let's see, what do I got? I got the point -1, 0, up to over 1, up to over 1, up to over 1, up to over 1, something like this. And I want to go from 1 to 4. So I want that area right there. So I'll just set up a simple Riemann sum for a small n, and then we'll try that with a general n and see if we can take the limit. So let's say for this first part here, I want n to equal 3. A nice easy one. So then my delta x, that's just the width of the interval. 4 minus 1 is 3. Then, oh, what am I missing there? Divided by n. So my delta x is 1. Right, the width divided by how many rectangles? Xi's, let's suppose we're going to use right-hand endpoints. Right-hand endpoint is always the starting value plus delta x times I. It's the easiest one to set up. So our starting value here is 1. Our delta x is 1. So we just get 1 plus I for our delta x's here. Right? And again, let's see if that makes sense. If I'm doing right-hand endpoints, then my first rectangle is going to be evaluated at 2. And I'm selecting 2 for that x value. And if I plug in I equals 1 here, I get the x value 2. So usually when I'm setting it up, I double check. Does that really work? If I plug in an I, is it going to give me the right x value I want?
What's that? The underneath, what's the 1 plus 1? What's that next to?
Here?
One.
Delta x is 1, and that's a messy I right there. Good question. And that's an I right there. All right, so next thing we need to do is to set up the Riemann sum, we need to know what's the function value there. So then we just plug that in. So what is f of xi? Well, I'll just replace I with what we have. So that'd be 2 times 1 plus I minus 1. And sometimes it's worth cleaning that up. So might as well, I can distribute the 2 pretty easy. That's going to give me 2 plus 2I minus 1, which is just 2I plus 1. Looks like my sketch is a little inaccurate. That rectangle should be more like that right there. The first I equals 1 gives me 2 plus 1 is 3 for that y value. So that makes sense according to my picture if it was a little neater. And so the Riemann sum here is the sum as I goes from 1 to 3, because that's my n. My delta x is 1 times my function value 2I plus 1. Now, for small n's, you don't really need the sum notation. The sum notation is really for n equals some big number, 10, 100, 1,000, where we don't want to write them up. But we could easily just look at this picture and write those up, because we should be able to find the points on this graph that we're using. So I should be able to look at this picture and say, oh, the first height is 3, the next height is 5, and the next height is 7. So my areas here are just 1 by 3, 1 by 7, or sorry, 1 by 5, and then 1 by 7. So I can look and get my area approximation with R3, right endpoints, 3 rectangles. According to my picture, it's just 3 plus 5 plus 7. So when you're trying to come up with formulas like this, use a couple of values for x and y to see, yeah, is my formula coming up with what I should be coming up on the graph? Does that work? Does this formula really match that right there? Did I set it up right? Well, if I plug in I equals 1, I'm going to get 2 times 1 plus 1, which is 3. And then I would switch to I equals 2. 2 times 2 is 4, plus 1 is 5. Yeah, this looks to be giving me just what the picture shows me I should be getting. Question?
Are we gonna have to memorize the shortcut formulas for sigma or?
No,
Okay.
you are not. Yeah, if you need those, I will give them to you.
Okay.
So, and we'll get to those in just a minute. Yeah, so the shortcut formulas for sigma, let's do that next. So again, this one's not that bad. I can see that the area is 15 for the 5th right-hand rectangle approximation. Is that reasonable according to the picture? Yeah, that's, the area is actually a trapezoid. Right? And the trapezoid, if I look at it sideways, has a height of 3 and bases of 1 and 7. And so for trapezoids, you average the bases. Right? So that would give me 7 plus 1 is 8. Average 8, you get 4. 4 times 4 is 16. Should be the actual area. Did I do that right? I think so. Oh, that's interesting. Shouldn't I have an overestimate? Where's my error?
I think maybe your graph's a little off. Maybe
My
is
graph is off.
could that be it?
4 times 2 is 8, minus 1 is 7. So that should be the right-hand endpoint here, right?
Yeah.
1 times 2 is 2, minus 1 is 1, so that's right there. And then the heights here should be 3, 5, 7.
The base could be 3 instead of the base.
Oh, the base is 3, not 4. Yes, thank you. So the area then is 4 times 3 or 12. There we go. Yeah, I should have written that out. So again, I was estimating this by thinking that this is a trapezoid with a base here of 1, a base there of 7. And then the height of the trapezoid would be 3. So the area would be 1 plus 7 over 2 times 3, which is 4 times 3 or 12. Yeah, so the actual area is 12. My right-hand endpoint is an overestimate of 15. All right, so let's do it again. This time we're going to let n be n and see what happens. So starting with f of x equals 2x minus 1 on the interval from 1 to 4, we're just going to go with n subintervals. The x is always the width of the interval divided by the number of rectangles. So for us, that's 4 minus 1 or 3 over n. Let's use right-hand endpoints to make it easier. So xi is going to be starting with the left side, take delta x times I. So for us, that's going to be 1 plus 3 over n times I, which doesn't clean up much. I could say it's 1 plus 3i over n. And I don't think it's worth finding common denominator. What's f of x then? Or f of xi? Well, let's plug that in. That would be just 2 times 1 plus 3i over n and minus 1. And that cleans up a little bit. 2 times 1 is 2, then minus 1 is going to be 1. Plus 2 times 3i is 6i over n. So just distributing the 2, combine the negative 1. And Riemann sum, again, is base times height. So my sum then, so this would be called Rn, right? Because I'm using right endpoints, is delta x times my function value. I there over, oops, sloppy there. Just that's divided by n. Reminder, what is the variable the sum is using? I. So everything else is a constant according to the sum. For example, the multiple here of 3 over n, I can pull that out instead of distributing it through. So I can rewrite this. And again, but that is the sum formula, right? So I could just plug this into Desmos, pick a number for n, like 100 or 1,000, replace that in there, and there, and Desmos will just pop out what the sum is for any number n. Okay. We want to take it a step farther and see if we can take the limit of this. We're going to try to apply that limit definition of the definite interval. So we should clean it up some more. So we're going to pull out the 3 over n. Let's write it down. Then we have 3 over n times the sum, as I goes from 1 to n, of 1 plus 6I over n. What else should I do with that? We can,
Could split up.
yeah, split up the sum on the addition. So we can break it into 2 different sums. So I'm just going to do that on another page, or I'll just shift this one up actually. So we're going to get the 3 over n times the sum, sum as I goes from 1 to n of just 1, sorry, not I, 1, plus 3 over n times the sum as I goes from 1 to n of 6I over n. And then Adam had asked about sum formulas. What sum formulas do you need to know? I will give them to you on the test. So the sum of I, the sum of I squared, and so on. What about adding 1 over and over again? 1 plus 1 plus 1 plus 1 plus 1. It's just whenever n is, right? So this one right here is pretty easy. That right there just adds up to n. 1 plus 1 plus 1 n times. So that's cool. This one right here requires a little bit more work. So let's see, cleaning up this side here, I have 3 over n times n. So all of that adds up to just a 3 plus, remember the variable here is I, which means the multiple of 6 can be pulled out and the divisor of n can be pulled out. So I'm going to pull out 6 times 3 is 18. N times n is n squared. So then what's left is to just add up I as I goes from 1 to n. And that formula I will give you on the test. Blue, the sum of I from 1 to n is n times n plus 1 over 2. So now I know that sum too. Scoot this up a little bit. Scoot that down. Oops, I missed. And now I'm going to write it over here. We've got 3 plus 18 over n squared times n plus 1 over 2. And the sum's all gone. So a couple of options. Now, instead of using a sum on Desmos or GeoGebra, I could just plug in n equals 100 or n equals 1,000, and that's going to be the Riemann sum for whatever n I pick. Or I could take the limit of that and get the actual area. All right, help me out here. The limit of 3 as n goes to infinity. 3. This next part's a little bit trickier. Here I have a rational function that's a polynomial over a polynomial, but it's n squared over n squared. Whenever you have the same degree top and bottom, it's the leading coefficient of the top and the bottom. Well, in the top, we're going to multiply 18 times n, blah, blah, blah. So the leading coefficient there is 18. Oops. Oops. So there's going to be an 18 on the top, and on the bottom, we have a 2n squared. So the bottom coefficient is 2. See, 18/2 is 9. 3 plus 9 is 12. Well, it's a fair amount of work. Right, so this is where the definite integral comes from. Fortunately, we discovered the fundamental theorem of calculus. Anybody remember what that tells us? It tells us antiderivatives will give you the same answer.
They
So-
they did all this work.
Well, the fundamental theorem comes from a Riemann sum. That's the way they discovered it.
Yeah.
Yeah. So, and I went over that the other day in class. It's a nice discovery because this is very hard.
Yes.
All right, so let's check this answer one more time. So we looked at it, we could do it geometrically in that case, right? Because the area happened to form a trapezoid. It's not always that nice, like a parabola. That's not as easy. There's not a geometric formula for that without using calculus. But let's check with the antiderivative. So next, fundamental theorem of calculus says that if you take the integral of some function little f of x dx from a to b for x, and you know some other function big F, actually I don't like using big F, I like using an a, you know some other function a of x, that's my area function. If a's derivative happens to be that little f of x, then that means big A is an antiderivative. And the fundamental theorem of calculus says, well, the answer to that definite integral is just that function, antiderivative function evaluated on the right minus that same function evaluated on the left. Right, bless you. The essence of the fundamental theorem of calculus right there. So applying it to our problem, integral as x goes from a, from 1 to 4 of 2x minus 1 dx. If I can come up with a function that is an antiderivative of that, well, what's an antiderivative for 2x?
X squared.
X squared, right? Because the derivative of x squared is 2x, and a derivative for negative 1, negative x. And then if you're going to set these two equal, then you have to write on the other side a 1 and a 4 for the bracket. Otherwise, they're not quite equal. And then fundamental theorem says just plug in the 4. And then subtract, plugging in the 1. And that should be the answer. So let's see. 16 minus 4 minus 0 is 12. Oof, I like that way better.
Yeah. So
Hit record. Oh, no, there it is. Stop this one. We'll do another.